So as we're evaluating, what do we want to be looking for? Well, we want to look for, if we have a high load, we'd like to see a high throughput, especially if we're dealing with small messages, which are our intended target. If we have a light load, we'd like to make sure we have low latency. And we'd also like to see that the throughput is proportional to the number of cores. So we don't stall out in some way, in some non-scaling fashion. Let's look at a low latency test. Okay, so this one is low latency. And what we're doing is we're sending a single message. And this message is ping-ponged between two servers on a 10 megabit connection. So if we look at the latency for, let's say, a 64-byte message, okay, we're looking here, so what we see is there were 3 different tests. So we can be doing Linux to Linux, right? So that is in the blue here. And then we have MTCP to MTCP, which is another test. And then finally here, we've got our IX to IX. They also did, I think, IX to Linux. So if we looked, for instance, if we're going the latency, which is not on this graph, so for a 64-byte message between 2 IX servers was 5.7 microseconds. And between 2 Linux was 24 microseconds. Right, so almost a complete order of magnitude difference between them. And then we see that our gigabits per second are, this is crazy, so it's not 10 megabits, it's 10 gigabits, right? It's a fast connection. So it's a 10 gigabit connection. And we can see that we're getting, for smaller packet sizes, like let's say this is about 50 or 60, we're almost to 7 megabits. And up here, we're approaching, let's say 9. Okay. This is good put. So good put is what is known as the throughput, the useful throughput. So it's the app level throughput. It ignores any retransmissions of packets. It ignores any packet headers, right? Checksums, all that stuff. It's the useful stuff. We get the good part of the throughput, right? It doesn't really do us any good to say, well, we completely filled up this 10 gigabit connection, but it was mostly with packet retries. And so the application didn't actually get too much. We are actually probably achieving the best achievable good put, or we're close to it. So we have right here about a 10% overhead. Maybe we could get less than that if we had even larger message sizes, but that's not so bad. And here we look at the overhead, because basically, for instance, much of a packet is a fixed size. And so when you have a very, very small message, the overhead of the packet is very large. So it might be, 10 to 1, let's say, which is why we're getting such a low good put here. So why does IX beat Linux? Well, several reasons. One, the latency is limited because of the fact we're calling run IO so often, and it's going to basically see message sooner than the interrupt is going to be. And there's no cost for interrupt, for queuing, for sleep wake up. All right, let's also look at multi-core scalability. So for multi-core scalability, what we can see here is the Linux. So let's see if we can mark these. What's the best one? Well, this one is 40 gigabits, okay, in IX. And we see beautiful scaling, okay, in terms of messages per second. Here, we are at 10 gigabits per second. And there, what we have probably done here is maxed out our 10 gigabit. The Linux is way down below. So this is both Linux 10 and 40 is about the same. And then MTCP is this other one, which roughly is scaling, but certainly is not getting the results as good as the IX. So there are many architectural decisions that IX makes different. First, we have a per application network stack instead of a single shared network stack across all applications. Not only is it per application network stack, it's actually a per application thread network stack. And that way, one of the things we get on that is our zero copy very simply. A second is dedicated cores. So each application thread has a dedicated core, and that way we don't do the multiplexing. That allows the polling and the run to completion. It makes the software more efficient and simpler at the expense of multiple cores, right? And that is definitely the cost of this. But we do get nice both latency and throughput, or even better, goodput. The other thing we are dedicating is not only dedicating a CPU core to each thread, we're also dedicating a NIC queue. So we not have a shared queue that's multiplexed by the kernel, instead just this single queue. Not sharing it means, again, we don't need any lock on the shared queue. That requires plentiful NIC queues. So for plentiful NIC queues, you will need a NIC that will provide enough queues, or you might actually have multiple NICs, that is multiple Ethernet cards in your hardware. There are some facts. So one is, what's adaptive batching? Right? The idea of adaptive batching is you never wait for packets. Right? There is an upper bound on the size of a batch, because if you can imagine that the run IO has a large batch and is running slowly, then the next time it could have a larger batch and a larger batch. It's kind of like the, I don't know, the snake that's trying to swallow, a python swallowing a big pig or something, right? It's hard for it to get down. And so we are going to have an upper bound on the size of the batch. We'll just throw away packets if the application can't handle them or it exceeds the size of that batch. And what will happen then? Well, again, the TCP/IP connection will slow down. It'll be as if it's just not getting a response, and the response to that, and what the other end will do in response to that is not send as much data as quickly. When do you not necessarily want high throughput and low latency? If you're not willing to pay the price, right? Sometimes latency doesn't matter. I know the rule of thumb that we had when I was at Google was you wanted a response within 100 milliseconds was when you wanted a web service to respond. More than 100 milliseconds, and they've done plenty of experiments that show users give up after a while, that it affects their usability if it's more than 100 milliseconds. So that latency really does matter. If you can afford lots of machines, high throughput doesn't matter as much. One question is, what's a data plane? So that's the code that's responsible for manipulating the packets. The control plane is sort of above that and decides things like, the NIC queues and what's going where and so on. The paper mentions a hardware OS mismatch, and that's just the fact that hardware does actually support high throughput and low latency, but many OSs are not designed to use the hardware to its full advantage. The trade-offs of using IX, other than just being able to run, well, you're not even limited to one app, right? You could certainly have multiple applications running on top of the IX kernel. We just happen to show multiple threads to the same application, but those could have just as easily been multiple threads from different applications. The trade-off of using IX is really a different API, and you have these possibly underutilized or wasted cores. There was a mention about RDMA in the paper. So RDMA is user-level reads and writes of remote memory. So the idea is you can use this, let's say, instead of TCP/IP, just provide memory-mapped remote memory. And what happens is you can actually set up your NIC to be supporting that. So you request local memory, the NIC sees that, it actually sends a request from the local NIC to the remote NIC to the memory and gets it back. It doesn't even go through the OS, so it bypasses the OS and goes directly to the memory bus without the OS's need or knowledge. So that is what RDMA is, but it's only normally used in a single data center because you'd want it to be fast.